So now the lift's finished accelerating upwards and it travels upwards with a constant speed till it gets close to its destination. Now let's consider what the scales read while it's travelling upwards at a constant speed. Well, it's always going in the same direction upwards, so that constant speed is also a constant velocity. And Newton's first law tells us that if something's moving with a constant velocity, then there's no unbalanced forces on it. So if there's no unbalanced forces acting on the man or the scales, then we know that the weight force of the man must be equal to the reaction force, which is applied on him from the scales. And so since he had a mass of 80 kilograms, those scales would read 80 kilograms while the lift travelled upwards with a constant velocity. Okay, now the lift is approaching its destination. As it gets close to the floor the man wants, the lift starts to slow down. Imagine that it was travelling upwards with a constant velocity of 2 meters per second. It then slows down to a stop, and it takes 2 seconds to slow down this much. So if the acceleration or deceleration is constant over this time period, what would the scales read? Let's look at how we could calculate that. Okay, so here's the lift with the scales and the man. The lift is travelling upwards, but it is slowing down. So that tells us that the acceleration is actually in the opposite direction to this velocity, because that's what we need to make this become slower. So the acceleration is actually downwards. Now, in order to work out the normal reaction force from the scales on the man, which is what we need to work out what the scales are going to read, we're going to need to know what this acceleration is. So in order to calculate that, we're going to need to go back and use our kinematic equations that we covered in the last topic. So we're told that the lift slows down in 2.0 seconds and that its initial speed was equal to 2.0 meters per second upwards. And we know that it comes to rest, so its final velocity is 0. So we're going to need to use the equation V is equal to V naught plus AT. So V is 0, V naught is 2, A is what we're trying to find, and T is 2. So we've got that 2A is equal to 2, and we've lost a negative. When we move this over to this side, we get a negative. So the acceleration is equal to 2 divided by minus 2, which is minus 1.0 meters per second per second. Okay, so now what we'll do is we'll use Newton's second law, which tells us that the acceleration is equal to the net force over the mass, and this is the net force on the man over the mass of the man and the acceleration of the man. So we know that 1.0 meters per second downwards, so that negative sign is represented by this downwards, is equal to the net force on the man, which is mg downwards, plus the normal reaction force upwards. So he's got this normal force and he's got mg, and these are the only two forces acting on him, and as a result of these two forces he undergoes this acceleration, and then we need to divide by the mass of the man. So we've got that 1 times the mass of the man, or the mass of the man in newtons going downwards, is equal to mg downwards plus the normal force upwards, and so the normal force upwards is equal to the mass of the man downwards minus mg downwards. So this is equal to, when we have a negative mg, this becomes an mg upwards, so this is m, and we've got g upwards plus 1 downwards, so these cancel each other out. We would have 9.8 and 1, and this would be the resultant here. So this would be equal to m, which is 80, times 9.8 minus 1, which is the 8.8, and that is upwards. And so we've got that our normal reaction force is equal to 80 times 8.8, which is equal to 704 newtons upwards. So now we need to work out what the scales read. To convert from the force in newtons to what the scale actually reads, we just need to divide by 9.8. So reading on scales is 704 over 9.8, which is equal to 71.8 kilograms. So slightly less than his normal 80 kilograms. So this is why when the lift is moving up and it slows down, you feel a little bit lighter. The floor is not pushing on your feet with as much force as it was when it was traveling with a constant velocity.